Because it was really quiet. These work.
There's some notes sitting right there if anyone needs them. Okay, so I already made my first mistake of the year, and originally I scheduled a work day for today, but like I was expecting you guys to be able to start working on your first assignment, but we should talk about factoring first. So I flipped a couple days around in the schedule. So although we're going to do a lesson today, it actually makes next week kind of nice. Next week we're basically going to have 3 work days to work on your assignment, and one more lesson on something called the quadratic formula. So it means they'll have a lot of time to work on our first assignment. So some of you guys are volleyballers, correct?
Yeah.
Who's volleyballing? Okay. Do you guys know whether you'll be missing Fridays and stuff like that already? Or is that still too far in the future? Okay. Oh, okay. So that's still a ways away then? Okay. Usually I try to schedule Fridays as work days, but sometimes we'll do lessons. So, okay. Okay, let's get started, I guess. Factoring is something that you would have started to learn last year. You probably hated it, because everybody hates it. It sucks. Until it stops sucking because you get better at it, it will happen, I promise. But most people usually don't like it to start with. Basically, factoring is the opposite of expanding. So you know how expanding means to, like, take one of these 2 bracketed things and times everybody by each other. Most kids are pretty good at that. That's usually not as hard of a skill. This means going backwards. So the goal would be then to take something like this and return it back into this. And the reason why factoring is so important is because it's a useful skill in solving questions. Yesterday, we were working on something like this, which was pretty intimidating at first, but it got better, didn't it? Like, it wasn't that bad at the end of the day. Ultimately, what had to happen, though, was once you did all of your whatever, let's say you ended up with like 2x squared plus 5x plus 7 equals 2x squared plus 2x minus 1. The only way it was going to work is if I made the question so that this 2x squared and that 2x squared cancel. That make sense? Life doesn't work out that nicely, though, right? And so we need other tools to be able to solve things, because what if there was a 3x squared right here and a 5x squared right here? They wouldn't cancel. And so that's where factoring comes in. Does that make sense so far? So let's do some review of what hopefully you learned last year. Okay. Before I get to that, though, I want to introduce just the terminology we're going to use. So just a bunch of bolded words. You guys know the word polynomials? We're working with polynomials. More than one polynomial number, I don't know what nomial refers to. So usually we write polynomials like this, like 3x squared plus 2x plus 1. That's a polynomial. And here's how it fits this particular pattern. A would be 3, x would be x, and then n would be 2 in my example. You see how this one goes n minus 1? So whatever this exponent was, this exponent here is 1 lower than it. And you keep dropping the exponent down by 1 slowly but surely until eventually you get x to the 0. Do you guys know what x to the 0 means? 1. If you've never heard that before, x to the 0 is 1. Actually, anything to the 0 is 1. That's just a math definition. I guess you probably just have to be told it, I guess. So if you were to have d times x to the 0, if this thing here right here is 1, then it means you don't actually have any x's. Maybe that's a better way of thinking about it. If I tell you that you have 0 x's, this number right here has no x's. Does that make sense? So, now we're going to focus mostly on polynomials that go to the degree of 2, meaning that it only goes as high as x squareds. But sometimes we can get to x to the 3's and x to the 4's, and that might look like this: 4x to the 3 plus 2x squared plus 7. That's a polynomial. I skipped something, though. I didn't actually write an x to the 1 term, but technically I did. I wrote 0x to the 1's. So sometimes you can even skip a number if you want, just have 0 of them. That makes sense. Long story short, those are polynomials. So, we'll move on. Yeah, more examples. That's not important. Okay, our goal today, work on the difference between expanding, which is what we did yesterday, and now being able to go backwards and factor. So, if I were to try to do what we did yesterday and expand and go this way, let's just walk through some of the steps you would have done. You might have done x times x, which would give you x squared. You probably would have done x times -1, so that's negative x. You would have done 4 times x, which would be 4x. I'm going to throw a 1 there, actually. And you'd have done 1 times 4, which is -4. So far, so good? And the next step you would have done is you would have combined your like terms and made it x squared plus 3x minus 4. So what we need to do is be able to go up the other way. I'm hoping, I think you learned a trick. The trick to being able to factor something like this is you have to look for special numbers. Numbers that add and numbers that multiply. Is this something that sounds familiar? Okay, good. So typically what we do if we try to go backwards is we're looking for numbers that add to give the middle number, which would be 3. And we look for numbers that multiply to give the last number, which is -4. Does this ring a bell? Okay. So I almost always try to start with the multiply. The reason why is that it actually narrows things down a lot faster. There's a lot of numbers that could add to give 3. 1 and 2, 0 and 3, 100 and -97, 1,000,000 and -999,997. So like adding numbers are usually harder to work with. I would go with the multiplying numbers because there's only so many ways to multiply to get to -4. 2 and -2, but that won't get you to 3. Or 1 and 4, and one of them has to be negative. And that'll work. If you use a 1 and a 4, but you make the 1 be negative, those are our numbers. Does that make sense so far? Well, those numbers are these numbers. So if you wanted to go backwards, what we're now going to do is, you know how when we expanded, we had 4 terms, and 2 of the terms were able to merge into the middle number? If I were to restart this from the top then, if I used to have x squared plus 3x minus 4, I like to show it like this. Take your 3x, and we're actually going to split just that middle term into 2 numbers. And those 2 numbers are going to be -1x and 4x. Because isn't -1 and 4 still add up to give 3? Basically what we're doing is we're separating a 3-term trinomial into a 4-term polynomial expression. Then what I like to suggest to do is to cut it in half. Maybe fun to show you this. And then what you want to do is you want a common factor. Does this look familiar? Okay, good. So what is in common between x squared and 1x? And the only thing in common is actually x. And so if you factor out an x, being the thing in common, what you're left with is x minus 1. Because both terms have an x, so I'm like pulling out the x out of those terms. And then the remainder is if you pull an x out of x squared, there's still an x left. And if you pull an x out of -1x, there's, well, the x is gone, so you just have -1. Does that make sense? Do the same thing to the second half. What's in common between 4x and -4? 4. So pull out the 4, plus 4 technically. And what you're left with is x minus 1. If you do it correctly, what should happen is this and this should be the same. And that means you know you're doing it right. So then that is one of your binomials. And then the other binomial is the leftover base, which is x and plus 4. And we've now gone backwards. This is called factoring. There's actually a shortcut. You guys have probably learned the shortcut though. Once you find these numbers, -1 and plus 4, -1 and plus 4. You guys know that shortcut? So like if you can find these numbers right here, those will be the numbers you're going to have right here. Sometimes you can skip that middle step once you get the hang of it. Anything else? Okay, so let's do some practice on this. If I have examples, we'll try them. If not, then we'll... You know what? I don't have examples. Let's make one up. New slide. Okay, so let's try doing x squared plus 5x plus 6. Maybe I'll just walk you through another one right from the top, and then I'll have you guys try another one on your own end. So I'm making up a new one, so find somewhere else off to the side to write this. Okay, so in order to factor this, what we're looking to do is split this number up into two different numbers. We need to make the trinomial 3-term polynomial actually into 4 terms. And to do that, we need to find numbers that add and multiply. And so we need to add to give the middle number of 5, yet multiply to give the last number of 6. Fantastic. Now, just so you know, if you can handle that, technically the answer is going to be x plus 2x plus 3. But I want to show you why the answer is x plus 2x plus 3, because there's actually proof behind it. So take your trinomial and split it up into 4 terms. It actually doesn't matter which one becomes the 2 and which one becomes the 3, but you're basically splitting your 5 into pieces. This one right here should just be 2x. Then I suggest cut it in half. What we're going to do is we're going to try to find a common factor. This guy right here, the only thing in common is x. When you factor it out, you get x plus 2. Does that make sense, by the way? I haven't really covered common factor yet, but that's something you guys recognize. Please stop me if I lose you, okay? So then on the second half here, there's not an x in common, but there's a 3 in common. And if you factor out a 3, like basically you're dividing everything by 3, 6 divided by 3 will give you 2. I know I did it right, because I have the same thing in both sides. Technically what you're going to do here is you're then going to factor out the binomial. And so if you factor out the binomial, the leftovers are x plus 3. But again, like I said, if you can just get this numbers up here, and you just want to skip down to here's a 2 and here's a 3, here's a 2 and here's a 3, you're good to go. Okay, one more. You guys are doing the last one then. So you're looking for numbers that add to give 1. But like a lot of numbers add to give 1. 0 and 1. 2 and negative 1. 3 and negative 2, right? So I would suggest focus on the multiply numbers. So you need numbers that multiply to give negative 20. Anybody figure them out? Some combination of 5 and 4. Just gotta make sure you get the negative 1 in the right spot. So if it's 5 and 4, whoa, that's a 20. The negative 1 better be the 4. Does that work?
So then it's x minus 4 and x plus 4.
Fantastic, yeah. And if you want to go directly there, I'm fine with that. So like if you want to show those intermediary steps, that's fine. But like it's accepted in math that you can just go straight from here to here if you like. Does that work? Okay. So let's talk about how then to use the factoring skill to help solve a problem. Okay. Let's say that I gave you this now as an equation. So let's say it was x squared plus x minus 42, but it was equal to 0. So now I've thrown on an equal sign. Can you, kind of ignore what's down here because I know it shows you what you're going to do, but can you get x by itself when you have an x squared and an x? The answer is no, you can't. If all you have is x's, you can just put the number on the other side. If all you have is x squareds, you can try square rooting. But if you have an x squared and an x, you're kind of screwed. So that's why we need this method here. So usually what we suggest to do then is try factoring it. And this one factors nicely. We need numbers that add to give 1 and multiply to give negative 42, and it's 7 and negative 6. Does that factoring make sense so far?
So we just take out the 0 and factor it. Pretend like the 0 isn't there.
Just like pretend the equals 0 isn't there, yeah.
Yeah, and then
Okay.
we factor it.
Then factor. Okay. So it's still equal to 0. Go ahead.
Does it matter what side, like the 7 and the 6?
No, irrelevant. Okay. Here's the trick, though. You know how it's supposed to equal 0? What you really have is something times something to equal 0. Now, back to like, I don't know, when did you learn multiplying for the first time? Maybe grade 3? In order to get something to multiply and equal 0, one of the numbers has to equal 0 that you multiply. Does that make sense? So that means there's two possibilities. It means that either x plus 7 must have been your 0 number, or whatever x minus 6 is must have been your 0 number. Does that logic make sense? Like either this thing must have been the 0, or this thing must have been the 0. We don't know which one, but there's actually two answers. What ends up happening is when you write that out then, if x plus 7 must have given you 0, it's my science class, then x is negative 7. Or what if the x minus 6 was the thing that gave you the 0? Well, then x is 6. That makes sense.
So
What is it? Go ahead.
The answer is x equals minus 7 and x equals minus 6. I would just have to know.
Two answers. Yeah, that's where things start getting confusing is usually when you solve, there is an answer. Now there's two answers. And eventually we'll build up so that there's 3 or 4 or 5 or... Does that make sense? That's where we're starting to build to. So I've got some other exemplars here. Why don't we do this one over here first and just talk through what happened. I don't want to actually break through all the steps. I just threw it up there for you to see. Let's say that I asked you to solve what's written right here. Is it possible to get x by itself? The answer is no. You have x squareds and you have x's. Okay. So this is one of those scenarios where you're like, let's say there was an extra x squared over on this side here. You just would have canceled them. But there wasn't, so we're kind of screwed. Control Z. Okay. So what we need to do first, guaranteed, is we have to make it equal to 0 on one side. Because the only way that this works is if it's equal to 0, because in the logic of, well, this is 0 or this is 0, it only works if it equals 0. Does that make sense? So first step, bring everything to one side and make it equal to 0. So if you subtract this, oh, I think it brought everything that way, actually. So the x squared is still sitting right here. If you take minus 8x and you minus 2x more, it gives you the negative 10. And if you have 16 and you add 5, it gives you the 21. So far, so good? Okay. Then they factored it. And you're looking for numbers that added to give negative 10 and multiplied to give 21. And you can see that's a combination of 3's and 7's. Okay. If you can do this step here using factoring skills, then the last step is usually pretty straightforward. It means that this must have been 0. And the only way to make this thing equal to 0 is if x is 3. Or it means that this thing must have been 0, which means x must have been 7. So we get two answers. You follow that? Okay. This one here is the trickier one. The reason why is that there is a leading coefficient is the term we use. And this is probably the hardest thing to factor. It's a lot harder when there's a number sitting out front. You actually need a different method of doing that. Is that something you guys recognize?
I have a question about the one that you just did.
Yeah.
Couldn't you just, since there's an x on either side, cancel the x so that they're just numbers?
The
Just
top,
figure out what x squared is?
up top here.
Yeah.
The problem is the x's don't exactly cancel though because there's 8 on one side and 2 on the other though.
You can just take out the x just to make it 2 and negative 8.
But then you'd still have x squareds and you'd still have x's. That makes sense. There's no way of making it so that you either have x or that you have x squared. In this case, you have both. And because you have both, this is why this method is used. Okay, so what we need to do then is I need to remind you guys how to factor something like this where there's like a, we call it a leading coefficient. So here's what the answers are going to be, but we should kind of review the difference there. So I'm just make some more room down here. It's going to be 2x squared minus 7x plus 3. You know how you're doing that add multiply thing? You're still going to do that, only there's a slight twist. You're still looking for numbers that add to give minus 7, but you're looking for numbers that times to give 6. I don't know where the heck I got 6 from. Yeah, it's 3 times 2. It's this 3 right here times that 2 right there. Why didn't we do that before? The x squared was a 1. We were doing it actually. It's just since the number that was in front of the x squared up until now has always been a 1, we didn't really need to worry about it. But we're looking for numbers that are the last number and the first number multiplied together. So here's where this gets a bit trickier then. When you find those numbers are not the answers though. Like you can't just jump right down to the bottom. So to times to get 6, you can do 2s and 3s or 6s and 1s. So that's probably a combination of 6 and 1, I bet, right? But that won't give you -7 unless they're both negative. Does that make sense so far? Okay, so here you have to do it the long method. We're going to take this and split it up into the negative. I'll go -6 first, I guess. It doesn't actually matter which one goes first. But I'm going to pull my trinomial, I'm going to stretch it out and make it a quadnomial. I don't know, whatever 4 is. Cut it in half. What is in common between a 2 and a 6? 2. Technically 2 is what's in common. 3 is the leftovers. So factor out a 2, and you can also factor out an x. Does that make sense? The remaining part will be an x minus 3. And double check your work if you need to, right? 2x times x will give you 2x squared. 2x times minus 3 is -6x. This one's a bit trickier. We have to make this second bracket x minus 3. And the only way that's going to work is if you factor out a -1. I know it seems weird to kind of factor out 1. It's like, why would you take out a 1? But if I leave this the way it is, it's not exactly the same as that. But if I factor out a -1, -1 times x will give me my -1x. And then -1 times -3 makes it +3. All right, so now I'm finally done. The thing in common was the x minus 3. The leftover bit was 2x minus 1. Does that look familiar for factoring? This is like the hardest thing that you probably did last year, or one of the hardest things. It's factoring trinomials like this. The whole time this stuff was equal to 0, by the way. I just hadn't been writing it, but it was equal to 0. So now it means 2 things. It means either x minus 3 was equal to 0, or 2x minus 1 was equal to 0. Because that's the only way that these two numbers can multiply and make 0. So you sometimes I kind of branch them off to the side. I won't write it anymore because we have it up here. It means that this thing was equal to 0, or that thing was equal to 0. This guy's really easy. You just add 3 to both sides. Ta-da! Does that make sense? This guy here's a bit trickier. First, you're going to have to add 1 to both sides, and then you're going to have to divide by 2. And what ends up happening here is now we have an answer, but the answer is a fraction. That's it. That's the skill. Okay. If you can now take that skill and apply it to differing levels of situations, you're good to go. I've got a lot more examples to walk through. So, I mean, I might not do them all. We'll see how you guys do it.
Should we ever do anything more than a trinomial?
Yes.
Like this year?
Not this year. But yes, like basically what's going to happen from here on out is we just make it the next level up, right? So basically if you can ask the question, can we do it? We probably can. Makes sense? How are you guys doing so far? Give me like a thumbs up or down or in between. Like, how is your comfort level with what we've been doing so far? Mostly good. Okay, I'm going to jump ahead then. Let's find something challenging to try. Let's skip that. Okay, let's talk just a bit more about factoring real quick first, though. Sometimes just to try to help students with factoring in case you're not strong with it, I like to try to break it up into 4 different categories of factoring. I think of common factors, simple trinomials. I call these guys complex trinomials when there's a number sitting here. There's also something called a difference of squares. Do you guys remember difference of squares at all? Okay, well, let's walk through all 4 of these then. Here's a common factor. For a common factor, you're looking for something that every single term has in common, hence the name, right? So both of these terms have an x, so you can factor out an x. What else do these terms have in common numbers-wise? A 3, yeah. So you could factor out a 3 and an x, and it would leave you with x plus 2. Is that something you guys are comfortable with? Cool, moving on. Simple trinomials. These are the ones where all you really have to do is find the magic numbers that make it work. Like, we need numbers that add to give 3. We need numbers that multiply to give 2. And if I can find those numbers, I can just go right to my answer. Anybody want to take a stab? You got it, 2 times 1. So it means your answer is x plus 1, x plus 2. I don't care which order those go in, by the way, it's irrelevant. Make sense? Okay. This next one is the one that most people find difficult, the complex trinomials. So we actually do the same starting method. The only difference is this the exact one we just did, by the way? Is this that one back there? No, it's slightly different. Not by much, though. We need numbers that add to give 7, because that's the middle number. And we need numbers that multiply to give 6. 6 being 3 times 2. The first and last number multiplied. So that'll be 6 and 11. Here's the thing, though. You cannot do this. You can't just go right to x plus 6, x plus 1. That's wrong. And I can explain that in a couple different ways. But maybe the easiest one is to say, well, at some point you're going to do a 6 times a 1 if you FOILed it. 6 times 1 is 6, not 2. Make sense? So if you just quick do a double check your work, that's not going to work. So don't go right to there. What you do need to do, though, is take your trinomial and you have to stretch it apart and make it go 6x plus 1x plus, can I make that into a 2 somehow? There, that's a 2. Cut her in half. What's in common? 3x, good job. Yeah, I think you guys seem to know what you're doing here. This guy right here needs to be x plus 2. So then, what are you factoring out? Do you guys know? Fantastic. Yeah, you got to factor out a 1, basically, to make it work. So when you're done, it's x plus 2 next to 3x plus 1. I'll give you lots of practice sheets for this stuff, by the way. If you want practice, I'll get you practice. I think I already have, actually. Does that work so far? Okay, there's one last type of factoring then. It's called difference of squares. This one's a very unique situation. It occurs when, you know how when you have like a 4-term polynomial, sometimes we stretch it apart into 4 terms. Sometimes what could happen is those 4 terms, it could have been like, say, a plus 9x and a minus 9x. And what would happen is those 2 terms would kind of cancel each other, and you would have no middle term. Does that make sense? So that could be the possibility. What usually ends up happening here, then, is you only ever see 2 numbers. Both of these numbers are square rootable numbers. I think that's a word. So, like, you know how like 9 square roots to 3 and 16 to 4? 81 square roots to 9. So here's your answer. It's x plus 9, x minus 9. One is positive, one is negative. Because exactly what I just showed you there is what happened. If you actually FOIL this thing out, you'd get an x squared from doing that. You'd get a minus 81. But then when you do this guy right here, you'd get a plus 9x. But then when you do this guy here, you get a minus 9x. And they would have canceled each other out. So that's why what should have been a 3-term polynomial looks like a 2-term polynomial, because the middle 2 terms would have canceled each other. So, okay, let's do another one. X squared minus 16 just becomes x plus 4, because that's what 16 square roots do, and x minus 4. You guys ever seen that? Cool, okay. Let's try some hard questions then. Fast forward to here. Let's do this guy. See if you can find wherever this one is. So, similar to yesterday, our goal is to solve for x. What did we do yesterday? Expanded it all, yeah. So expand the crap out of this thing. Anything that can expand, expand it. See what happens. So, if you do that, this guy will give you an x squared. That guy will give you a 1x. That guy will give you a 2x. And that guy will give you a 2. And then this guy, when you expand it, you'll get an 8x and a minus 4. So far, so good? Okay. Yesterday, if we were going to solve things, the x squareds had to cancel on both sides. Do we have an x squared on both sides? Crap. Okay. New strategy. Okay. So the new strategy is now get a 0 and factor. That's your strategy. So bring everything to one side. So I'm going to recommend, let's take all this right-hand stuff over here and let's bring it to the left-hand side. So like minus 8x and add 4. Because now this side here will be equal to 0. Has to equal 0. Otherwise, this whole logic train doesn't really work. So you'll have 8x squared. Sorry, you'll have x squared. And then 1x and 2x would have been 3x, but you're subtracting 8, so you'll have negative 5x. It's a 5, by the way. And then 2 and 4 would have been 6. So far, so good? Okay. Now, we're going to refactor. So we need to look for numbers that add to give the middle of this thing, which is minus 5. And we need to look for numbers that multiply to give 6. 6 and 1 and 2 and 3 are the main ideas.
We do 6 and 1, and then we make the 1 negative.
The 1 negative? Or the 6 negative, actually. Good call, yeah. 6 and 1 works, but you gotta make the 6 negative. 2 and 3 do give 5, but like the negative sign doesn't work out, you know what I mean? Okay, so if you'd like to, you guys can hop right to this then. You can call it x minus 6, x plus 1 equals 0. Deb.
Like for the full number, you put the negative 2 x and negative 2x.
Like splitting this thing up there? I don't think negative 2, negative 3 work though, right? Because negative 2 and negative 3 do give negative 5. But negative 2 and negative 3, when you multiply them... Oh, hang on. Did I screw that up? I did screw that up. Thank you. Sorry, Shelby. I was wrong. It's not 6 and 1, is it? It's 2 and 3. Because we need a negative 2 and a negative 3 to make it negative 5. And then the two negatives make it positive 6. Thank you. Sorry. Good catch. Totally screwed it up. So change that. Make it x minus 2 and x minus 3. Teachers are people too. We make mistakes. I'll make lots of mistakes, by the way. For the next 2 years of working together, I will screw up a lot. You guys okay to that spot there then? Okay. So last step then. This is, in my opinion, I think this is a brilliant logic actually. If we force this side to be 0, that's the key. We have to force that side to be 0. One of these two things has to be 0. That's the only way you times to give 0, right? So it means that, if you want to write this out, x minus 2 had to have been 0. So that means x is 2. Or x minus 3 must have been 0. So then x is 3. There's actually two answers.
Would it be negative or positive?
Should be positive, hopefully. Because like if you put in a 2, 2 minus 2 would give you 0. Some people usually eventually figure out like a logic that says that if my factor is a negative 2, my answer is positive 2. That makes sense? Like after a while people start figuring out, okay, if this is a minus 3 as a factor, the answer is just 3. We can check our work, by the way, so that I can kind of just do this in our heads a little bit. 2 is supposed to be an answer. 2 plus 2 would have been 4. And 2 plus 1 would have been 3, correct? So 4 and 3 means this side here would be 12. You guys remember that? So then, I'm going to start on the inside here. 2 times 2 would be 4. Minus 1 would give you 3. And when you times it by that 4 sitting right there, it would be 12. So apparently 2 does work. Here's where math kind of gets a bit different. There's more than one right answer, apparently. So let's try 3 as well. 3 plus 2 would have given us 5. 3 plus 1 would have given us 4. Times those together, you'd have 20. Okay. 2 times 3 right here would have given you 6 minus 1 would give you 5, which times by 4 still gives you 20. Crazy. There's more than one right answer. What do you guys think? Something you can do?
Mm-hmm.
Well, go. Okay, try this one. It's hard. Maybe before you start, I'll give you one quick hint as to how to start. What does a squared sign mean? It means you have two of them right next to each other. So maybe a better way of writing this would be this. 3x plus 2 next to x plus 2. And then 13 next to another x plus 2 equals 12.
So if you've got x plus 2 and x plus 2, can you FOIL that and then take that bracket and times it each by 3?
Exactly, yeah. Yeah, so where you're going to start is you're going to FOIL everything to death, right? Start by FOILing this bad boy, times it all by 3, and then also FOIL this little bit here too. Eventually everything will now no longer be in brackets. Then you're going to make it equal to 0 and factor. So I'll give you guys a head start. See whether you can do it on your own. So I put 2 lines of work down here. If you want to take a look and see whether yours looks something similar to mine, this is what I've got so far. I FOILed out some stuff that I could, and I times it all by 3, and basically I've gotten to the point now where nothing has brackets anymore. And hopefully you have something similar to mine. I haven't combined my like terms yet, though. So maybe you'd combine like terms. But hopefully you can get to something similar to this. I lost you on a step there?
Why is it 6x instead of 2x or instead of 4x? So you do.
Right here? Oh, because did you put these two x's together and make it 4x?
Yeah.
Oh, I just left them separately. And so I just haven't combined these. So you might have the 12x?
Yeah.
Okay, that's all.
That's what I have.
Okay, so just pretend that my 2x's right here is just a 12x then. Then you have what I have.
Okay.
I just haven't combined my like terms yet. Hopefully at some point though, you'll have a whole string of stuff, right? Because everything has been like expanded. If I could give you an analogy, it might be like, let's say that you've got like a rope, and the rope is tied up in knots, like very unuseful knots. This is what we've just done. We've taken our rope and we've unknotted it all. And so it took us a long time to do all that stuff, right? And now we have a rope. And now what we're going to do is we're going to rearrange our rope and make an actual proper knot out of it.
Okay.
Meaning we're now going to go back and factor it.
So I should combine.
So what I'm going to suggest now is let's combine all of our like terms, get all of our numbers on one side, and make it into like a quadratic polynomial. So I'm going to suggest let's maybe bring the minus 12 to the other side. And let's see whether we can make it equal 0. So we've gotten rid of all of the brackets. This side is now 0. I just got to keep track of everything. You should have a 3x squared. That'll be this guy here. That'll be 12x minus 13x I've got negative 1x. Anybody else add those up and get negative 1? Okay. And then I've got a plus 12, but I've also got a minus 12. So that kind of cancels. So here's what I've got once I've kind of rearranged this thing. 3x squared minus 1x and minus 26. You guys with me so far?
Yeah.
Okay, so now take the next few minutes on your own if you can. Try factoring that thing. It's a challenge, don't get me wrong. You're looking for numbers that add to give negative 1 and multiply to give whatever 3 times minus 26 is. Yeah.
Oh, but you're not looking for it to multiply to get 26 because there's that 3 sitting out front. So you gotta do 26 times 3. That's what you're looking for. It's equal.
Okay, so you're looking for numbers that add to give minus 1, but you're looking for numbers that multiply to give, is it minus 72? Is that right?
Yeah. 78.
78. Ooh, that's gross. 78. Huh. What multiplies to give 78? Has anybody found numbers that work? Yeah, but that's about it. Because 78 will do 2 and 39? 2 and 39? 13? Right?
13 and 6.
That doesn't differ by 1. 7 and 8 won't work. 9 and 10. So,
I got the answer.
what'd you get?
I got 3x plus 1 in one bracket, and then x minus 26.
Okay, say that again.
So I use negative 78 and 1, because that's, and then I had, so 3x squared minus 78x on one side, and then plus 1x minus 26 on the other side.
That does
These two numbers here, though, don't equal 1, though. Right? Because like the way this is supposed to work is the minus 1 is supposed to split up into 2 even numbers there. And 78 and 1 doesn't do that.
I did have a negative 1
Yeah.
there.
Okay, I wonder whether maybe when I designed this question it was actually to make a point. And the point is that there is still things that can't be factored. And if you cannot find numbers like this, that's actually the goal of our next lesson. Okay. So what I've shown you so far is we can solve things by expanding. And by expanding, if all of your x squareds cancel on both sides, it's usually not bad. If they don't cancel on both sides, we can try, keyword here, try to factor. But there are some things that don't factor. And so there is a third method of how to solve things that I'm going to show you guys sometime next week. It's called the quadratic formula. And so in this case here, if it's not factorable, we actually do have a third backup method. So at this point here, I might actually have to say wait till later. Wait till quadratic formula. Maybe that's why I put this question on here, because I don't actually see any numbers that work.
I know that.
That being said, let's say that it was factorable. Hypothetically, let's say that you could somehow get it down to 3x plus 1 and x minus 2. Hypothetically. I know that's not the answer, right? Then does it make sense that you can turn this guy into an x equals 2? Okay. And this guy right here, it would be like 3x plus 1 equals 0. 3x would equal negative 1. There, we'd have our answer. So if we could have factored it, could you guys have solved it? Okay, so all that just mattered is I made you guys a question that wasn't factorable. So next week we'll learn how to solve those. Does that work? Okay, so quick summary then, and I'll let you guys take off if you want, or whatever. I guess lunch is starting soon. Here's what we've learned in the last, 3 days. I need you guys to have impeccable algebra skills. Like, you need to understand the idea that, like, you can add 4 to both sides. You can divide both sides by 2, right? If I can start doing some of those things a little bit faster, it certainly helps, right? That was day 1, using your algebra skills. Day 2, you need to be able to expand. And it could be like a 2 bracket next to a 2 bracket. It could be a 1 thing next to a 2 bracket. It could be, so long as you can expand. Expanding is often very useful because if you like my rope with knots analogy, you're kind of untangling everything. Rather than it looking so ugly with a million different brackets, we found a way to turn this ugly mess into like a nice line of just x's and x squareds and numbers. Right? If all the x squareds are gone, we're great. But if not, then we have to make it equal to 0. And if we make it equal to 0, and if we can use today's skill of factoring, we hopefully can solve, but we'll get 2 answers. That's okay. Next day then, the last thing we'll learn in this like set of lessons is if we can't factor it, there actually is still a backup method for solving. Does that make sense? Okay. Now you guys should be able to do some of the questions on the assignment. Not all of them, but a good chunk of them. You should have some skills to work on. So next week we'll have a bunch of work days to work on those. But maybe take a look and see if you can do the first couple if you have some free time. If not, you guys can kind of get ready to go. The bell should be going here in a bit. We've got lunch, so. Sound good? Yeah, cool. Thanks for a good first week, guys. I hope you didn't get scared away. Hope you learned stuff. Usually at the end of my notes, I always put down a slide of stuff. I always call it recommended practice problems. In case you want practice on stuff, by the way, here's a few pages in your book, and I give you guys some worksheets. Okay, so, again, completely just for if you need more practice. Okay, not to. Oh, go grab a textbook from Noni in the library at some point. Sorry, I don't take you guys down to do that. You guys are big kids. Find Noni at some point. Sorry, I forgot to mention that, I guess. Then. At some point in your life, go find a textbook. Yeah, no, you guys are pre-calculus 11. Eventually, I'll start like breaking up into -1 and -2 as you guys want to, but we'll do that in like another week or 2. All right, see you guys later.